trying to solve, and that is fluid flowing down a cylinder, and where a constant heat flux is provided. So the equation is, the general equation is given sort of the convective term, the steady state equation. This represents the convection here. The axial convection term is neglected, taking into account the length of the tube to be much larger than the radius. And then this is the viscous dissipation effect. Right? So all of this is following from the general energy balance equation on non-dimensional essays using the following variables, where we have the non-dimensional temperature given by and then we have the non-dimensional distance in the radio direction given by this, and then theta is the distance in the z direction, the non-dimensionalized distance, which is given by E z divided by when you do this, then the equation reduces to the following form, is 1 minus psi squared. This is the left-hand side here. So we are getting 1 minus psi squared comes in here, and then you have, instead of RC, we have psi, and then all of these parameters are contained now in the Brinkman's number, which is given by can be regarded as representing the effect of the viscous dissipation to that of the heating that is externally provided. The ratio of that, right, can be regarded as a measure, the ratio of the viscous, the energy transfer or the energy generation, viscous dissipation to the external heat transfer or flux that is provided in order to heat or cool the fluid. So Q naught greater than 0 would mean that the fluid is being heated. Q naught less than 0 means the fluid is actually being cooled, or its temperature is reduced as it flows down the tube, depending on the purpose that is required. So we took up the solution of when the viscous dissipation effect can, for instance, be neglected, in which case the equation reduces to this, but it still requires a little bit of effort to analytically solve it. Now the boundary conditions are given or can be easily reduced to the following. So here we need, sorry, this is theta. So we need one boundary condition in the z direction that could be given by is actually equal to 0. That is at the inlet. Here T is uniformly equal to T1. So at theta equal to 0, the dimension is temperature, because it has a T minus T1. boundary condition, and the second boundary condition is that the eta is finite at a psi equal to 0. We saw how that condition was made use of, and then the boundary condition at the surface of the cylinder would simply be psi equal to 1 is equal to actually Q naught. I'm sorry, it's actually to 1. It will turn out to be 1. Right? So that can be easily shown. So with these boundary conditions, what the problem can be fully solved, but what Boussinesq Lightfoot provides is the so-called long distance solution, which is represented by this. The C naught is a constant, so this is what he calls the asymptotic or now if you do this, then this is only an approximate, cannot be valid for the entire region. So then we get a differential equation in psi, and finally we get that psi can be, the function psi can be written as C naught by 2 times psi squared by 2 minus C2, and then I take that C1 must be 0 because the psi has to be finite at psi equal to 0, the radial distance equal to 0 at the center of the cube, that is. So then this condition, as I said, cannot really be used here because if I put theta equal to 0, right, then I get theta to be psi. So that cannot be used. However, I can use this condition and on the side now, and because this term won't contribute, so I get effectively this reduces to equal to 1 at psi equal to 1. That's what we get. And this leads to the determination of the constant C naught to be full. That is what we saw. So all of this is just a recap of what we have already done. Now for determining the constant C2, since I can't use this condition, what Boussinesq proposes an integral balance over the basically it amounts to integrating the energy balance, right? And then finally, and then neglecting the viscous dissipation term. And when we do that, the condition reduces to the following, namely that the integral balance leads to the following condition. And just tracing the approximations and the arguments, right? So integral condition would be to integral 0 to 1 psi so this is what the integral condition would lead to in terms of the reduced variable. Now, all of this, not all the steps I have derived rigorously, but you can easily verify that this is what you will get. Now, all I have to do is now substitute for this. Right? So C naught I know 4 theta plus psi, and psi I have this. So you can C2, which is to be determined, and then I have the rest of the terms. And C naught is 4. So this will be 2. So this would be psi squared, right, minus psi power 4 by 4. This has to be integrated, and so this has been integrated. So what you can see here is that you can easily verify that integral 0 to 1 minus d psi, which is what will be multiplying the quantity 4 times theta, which is to be regarded as a constant here, because the integration is only over psi, can be easily seen to be, so this would be psi squared by 2 minus psi power 4 by 4 evaluated between 0 and 1. So this would be 1 by 2 minus 1 by 4, which is 1 by 4. And so that is going to multiply 4 times theta. So that you get a theta here which will cancel with this, right? So, so we get theta is equal to theta. So that will get removed and we can then determine C2. So what we have then is we have C2 times integral 0 to 1 side of 1 minus psi square d psi, that is this term, plus integral 0 to 1, that doesn't have any other constant multiplying, but it is having psi times 1 minus psi square times psi square minus psi over 4 by 4. So this will get cancelled because we have clearly determined to be 1 over 4. So this will be C2 over 4. So this has to be calculated, right? So that's what I get if you calculate it is that it turns out to be 7 over 96. You just have to multiply. There doesn't seem to be any simpler way of doing it, any transformation, but you simply have to multiply it with all polynomials, so you can easily integrate it. So I get 7 over 96, and of course this is equal to 0. So C2 will be equal to minus 7 over 24, and so I can write the final solution as equal to 4 times theta plus psi squared minus psi power 4 by 24 is what I sorry. So I have psi squared minus psi power 4 by 4 plus C2, which is minus 7 over 24, seems to be what is the correct solution. Right, and so we have seen answered the accuracy of this is that for theta greater than 0.1, theta is predicted to within 2%. This is the validity of the large set approximation. Now there are other, I will directly those who are interested in following up on, for instance, what would happen to the actual solution, not just the large distance, how to find the actual solution, and also what happens when we introduce the viscous effects, if that becomes important, because we here making to this assumption, the Brinkman number is less than 0. So I refer you to a couple of journal articles which you must be able to access quite easily. And just give you the references. One is article, which also you can refer to. Same journal, that is volume 7, 386. So if you look at one or both of these papers, what they in this actually they've given a table where they've looked at different possible cases. So one case that I'm considering is for Prandtl number given by 1000, and then the Brinkman number can also be written, I guess, in terms of the Prandtl number and the Reynolds number. So what they are saying is the Reynolds number 2300 corresponds to laminar flow, and they find that Brinkman number is much less than 1, except for very narrow pipe diameter. We saw that the Brinkman number has a 1 over R, capital R, so R in the denominator, so it will increase as at very low values of the pipe diameter. So this is a good typical conditions they have given. In the table they have given a whole host of some practical conditions. You see, Prandtl number 1000 correspond to a liquid that's quite high, and but it corresponds to normal liquids. And so for laminar flow, they say that the Brinkman number is much less. So they've given a whole host of conditions for which the solution where the viscous effects are neglected will be applicable. So for Reynolds number very high turbulent region for this class of fluids, then they say the Brinkman number would be of the order of 100, and of course this varies depending on the pipe diameter, and so you would have to take into account the viscous effects, right? Then they also, one of these papers also provides how to get the solution when the viscous dissipation term has to be taken into account. So all kinds of generalizations are available in these papers, so you can take a look at that. The interesting situation is pointed out what happens when the Brinkman's number is actually less than 0. So if you look at the Brinkman's number, it has this, so how can it be less than 0? It can be provided if you're looking at cooling. So if Q0 is less than 0, then the Brinkman's number will be negative. So what happens is, if you, for instance, considering the fluid force flowing down, and let's consider the case where it is being heated, so that means Q0 is greater than 0, so I think the arrow so that the heat is input to the fluid and it's being heated, you can see the viscous dissipation is also going to increase it's also going to cause a heating effect. We've already seen that, how the nu times it's a square, dVz by dR is square, so it's positive. It's going to add towards increasing the temperature, right? So both the effects, when the fluid is being heated, both of them contribute towards increasing the temperature. So there's no counter effect. However, if on the other hand, if you are considering the case of cooling a liquid, it means Q0 is less than 0, so the arrow here points to heat being removed. On the one hand, you are removing the heat in order to cool the fluid, but the viscous dissipation effect is going to increase the temperature, so one has to be careful. And they obtain an interesting case where they have a Brinkman number, this is 0, so Brinkman number here would be less than 0. So they say that there is a critical Brinkman's number, right, below which, that is, you go further to the left, below which you would actually have a net heating rather than a cooling. So if you are taking a Brinkman's, this is the critical Brinkman's number. So if you are in this range, beyond this, right, so that means Q0, the magnitude of Q0 is not sufficient enough, so we are not removing as much heat as is required. So the viscous dissipation is sort of dominating over Q0, and actually the fluid is getting heated, whereas the purpose is of cooling the fluid. So you have to naught, removal, enough removal of heat, that means the magnitude of Q naught should be sufficiently high so as to shift the Brinkman's number to the right of the critical Brinkman's number. Of course, if you continue to be negative, they have to operate in this range so as to provide a net cooling. So this is an interesting situation that arises when you're interested in cooling the fluid, where there is a competing effect of the removal of heat on the one hand externally and on the viscous dissipation which contributes to heating the fluid action, which you cannot really avoid. That is going to happen. But by removing a sufficient number of heat, amount of heat, we can effectively reduce the temperature. So this is, you can see more details of these ideas in these papers. Are there any questions on the problem itself? Okay, if not, we will take up another example which would actually involve what is called as free convection. This is forced convection because the fluid is flowing. So we take another example which is called as free convection. And in effect, the flow is actually induced by temperature differences rather than being an external forced flow due to gravity or pumping of the fluid. That is what is referred as free convection. We will take up some of the problems that are in the latest assignment, variations of these problems that we have considered. One problem that I have considered just now. You can actually go and solve those problems based on whatever ideas we have encountered. We will take them up later, but now I want to consider a counter example of free convection. And there again I have given a problem that is a variation of what we are going to consider. That problem I take up now in the rectangular coordinate system. So free convection. These are an examples of Lightfoot. So I just want to point out the overall details, overall structure. So what I have is two walls. You can consider them as two parallel walls, which is being heated, and so the temperature of this wall is T2, and temperature, let's say, here is T1. That is being heated, so the axis, this is the organ in the bottom of the system. So you can, because this is some kind of a container which is bounded by these walls, and so the y-axis is this one along the length, and this is minus b and this is plus b, and this is the z-axis is the vertical direction. So this is what we have. So now, if you look at the energy balance, which is the one of concern here, energy balance would be simply OCB equal to plus the viscous dissipation effect, which we have to evaluate in this case. So again, so many approximations are considered, so we won't really be looking. So effectively what Lightfoot would say, because there is no forced flow, the system will be quite negligible coming out of convection, the forced convective effect. And because of that, the viscous dissipation also can be neglected, right? And so only it will be like a pure convection. The temperature profile can be obtained without solving for the velocity approximating. And then he considers that T equal to T of y alone. So the temperature variation is only in this direction. There is no temperature variation in the z or in the x direction. This is like a one-dimensional heat conduction. This is not the main point. What effect this has on the velocity profile is what is of concern, right? In field convection. So it is considered a very simple system. So this would mean that E square T by dy square into 0. We know the well-known linear velocity profile. If we get a heat connection in a solid, actually, this is only an approximation. So, if this is higher than this, then the temperature profile is going to look like this, and then he writes the temperature profile itself can be written as T1 plus T2 by 2 minus half times T2 minus T1 y over v. So you can clearly see that when y is equal to v, right, you should get T2, T1 rather, y equal to minus v, you should get T2. That will satisfy the boundary condition. So he then defines this as T bar, an average temperature T1 plus T2 by 2 minus half delta T, that's a difference in temperature, times y over v. This is the temperature profile. Now what effect this will have? The velocity profile is what we want to see. And here, one important approximation, the effect of the fact that the fluid, even though it's treated approximately as incompressible, is an effect of the density variation that has to be considered to what is known as the Boussinesq approximation. So that is what will be the important point of this example, and how that is introduced, and some contradictions in the approximation, but we have to accept it and use it. Now you can ask what will be the equation of motion that would look like in the, basically we are looking at the z direction only, right? You can apply the equation of motion in the other directions. If you look at the z direction, z component of the momentum balance, what you will get, the inertial terms, you can neglect, probably they all vanish because this is only, so again, Vz is assumed to be a function of y alone. So there is only one dimensional flow because this is E there. The fluid here is going to rise, and then, because it is cooled, it is going to come down. So there will be a flow induced by the differential heating of the two plates, right? That is what would happen. So the inertial terms based on these approximations you can easily verify will vanish, and so what will be there on the right hand side is minus dP by dz. So you should verify that the pressure variation in the x and y direction probably will be zero. That may be what we get a net effect of the momentum balance in the x and y direction, right? And then we have the effect with the body force, that would be minus rho g, and then I have plus the viscous term would be the Laplacian of the v in the z direction. That's how you're going to get. Very simple idea. Now the important point here is that there is now the temperature effect. We have said that the viscosity dependence on temperature is neglected. So the temperature effect is coming because now the density, to capture the minimal effect of the free temperature, you have to now account for the effect of temperature on the density. This is like a, probably regarded as a compressible fluid, right, in this sense. Now, of course, if you allow the density to change, and then you have taken about the continuity equation, because the continuity equation will no longer be just the divergence of V equal to 0. But that is not what is being done. That is being retained, and the temperature effect on the density is considered only in this equation. Now, this is the Boussinesq approximation, which is that the rho at a given temperature is given by the rho at some average temperature characteristic temperature. You can also expand basically a first order expansion of the density with respect to temperature and neglecting all the higher order terms. So clearly this would be d rho by dt at t equal to t prime. This is all there is. Actually, there is nothing much to the Boussinesq approximation. It's just an expansion of considering the minimal variation of temperature. You expand it with respect to temperature and take only the first order term. However, this quantity d rho by dt as a thermodynamic, because this is now effectively looking like a compressible fluid, right? And you can easily show that this is actually can be written as rho bar. This I call it as rho bar, right? Times 1 minus beta bar times T minus T bar. Beta bar is the coefficient of thermal expansion, which anyone who's taken a course in thermodynamics would know. Coefficient of thermal expansion evaluated at the mean temperature. That is what beta bar is. Beta, if you recall the thermodynamics, is 1 over V dV by dt at T, coefficient of thermal expansion. That is the change in volume or specific volume affected by temperature at constant pressure and per unit volume. So typically, when you're considering fluids in thermodynamics, we choose this as the molar volume, specific volume. But because I have V here and I have V here, I might actually regard V here as the specific volume per unit mass, right? So what is the relation to density? What we want here is the density. So V has an inverse relation to density. So here I am regarding it as the volume per unit mass. The definition would hold because I am dividing by V. So if I regard this as the molar volume, then this would also be the molar volume. If I regard it as the volume per unit mass, then this would also be. So I am not changing the notation here. I am regarding here V as volume per unit mass. This is clearly to do the inverse of the density. And so this can be written as now dV by dt then clearly is equal to minus 1 over rho square d rho by dt. Right, so beta itself would be 1 over v would be simply rho times minus 1 over rho square d rho by dt. Also the constant pressure, and here the way it is written normally consider it effectively, if you want, I can regard this as an expansion at constant pressure also, but the effect of pressure on the density here is neglected. So effectively, this is minus 1 over rho. So effectively, I am replacing d rho by dt at t equal to t bar as simply minus rho beta, and evaluated at t equal to t bar would mean this is also evaluated at t equal to t bar, which is minus rho bar beta bar. That's exactly what I have written here. So I can write this as rho bar, right? And then just sort of forgetting the fact that it's a derivative very constant pressure, we suppress that for the moment, and then I can write this as d rho by dt at t equal to t bar is minus rho bar beta bar times t minus t bar, which then can be written as rho bar times 1 minus beta bar times t minus t bar. This is the Boussinesq approximation. This is where the temperature influence on the velocity is going to come. Otherwise, it just looks like the equation of motion for an incompressible fluid, which we have already solved. So the crucial point is here is coming that when I substitute this and then I get the t from here. So let's just do that. Right? So what I will get then, now we have to solve for the velocity profile induced by this differential dt. Right? So minus 2 times d squared dz by dy square is dp by dz. You can already see the contradiction. On the one hand, the density is allowed to vary. That means it is not strictly being considered as an incompressible fluid. But when you consider that case, then the pressure we would think is no longer a mechanical variable. However, that is being dictated. This is quite a contradictory, and you cannot probe very deeply into it. But you just accept it as it is, and then proceed, because then the pressure also has to be is a function of flow and temperature for a compressible fluid. So it seems like selectively it is being applied there for the density. The rest of the thing you just assume that the fluid is behaving like an incompressible fluid. Right? So plus rho g, and so here is where I g times rho bar times 1 minus beta bar t minus t bar. This is what we have. And so what would happen then is, because we need to solve this, right? So this is a function of z alone. This is the function of y alone. T again is assumed to be a function of y alone, the way the convection equation is written, right? So we obviously want to bring the temperature term to this side, and then we can solve it. So this would be minus rho bar g times 1 minus beta bar, and then t minus t bar is minus half delta t y by d, right? Minus half. So is equal to dp by dz. So now I see that this is a function of y alone, this is a function of z alone, and I can equate it to some constant, which here, I think the way he has done it is actually bring the rho bar g also to that side as a typical version, because that will give rise to the effective pressure. So that is anyway a constant, so I can bring it anyway like 1. So what he finally finds, we need to be clear as to what the constant is. Right? So what he is doing is rho bar beta bar g. I have a plus here and then I have a minus. Right? So that would be minus. I am writing this term now. Minus rho bar g times minus beta bar. And then there is another minus here. That finally lead to a minus. And then I have a 2 delta t y over b is equal to dp by dz plus rho bar g. That's anyway a constant. I can move it whichever way I want. Right? So I will call this some constant C1. So this is basically a second order differential equation in y. There is really nothing too much complicated than integrating it. So now what I need to consider is that differential equation. I just have to integrate it equal to C1, right? So first time if I integrate it, I get minus half, and then this will be integrating once, we give it y squared by 2. Is equal to C1 y. Now I integrate it another time, right? So I get 2 times dz the 4 actually. Y squared, right? So that would be y cubed by 3 is equal to C1 y squared by 2 plus C2. This is the final form. So I can easily write it, as in terms of the velocity itself, right? So C1 plus, we need to get another constant. Okay, this C1y plus C2, yeah, this is a constant I missed. So this would be C1 y squared by 2 to C2y plus C3. That is what I have. So I can write here, just in case you are able to see it clearly, is equal to 1 over 4 over minus actually 1 over 12 y cubed. So when the minus goes into plus C1 y squared by 2 C2y plus C3. So there are now 3 constants, but we have only 2 boundary conditions effectively. The boundary conditions are clearly the no-slip boundary conditions can be applied. I guess that's what they're doing, right? So that again is a question. I mean, when you're dealing with gases, whether that's really valid or not, but we apply that. So y equal to minus b, dz equal to 0, and y equal to plus b, dz also again is equal to 0. The 2 of the constants can be determined, and then finally to determine the third constant, what Lightfoot argues, again they use an approximation. I write down, we're running out of time. So finally what we will get, I'll just determine, once the constants are determined, I'll just write the final answer. That's quite easy to, looks complicated, but 2 of the constants, effectively C2 and C3 you will find can be determined by those 2 conditions. So I'm just going to write the final solution. So the dz would be over G plus come about, but this looks like the final form. I think it is probably this is I think it's 12 or 2. Probably just 2. Right? This is 2. I'll check this again. This is, you can verify this. So this is where we would be. If you determine, apply the no-slip boundary conditions, 2 of these constants can be determined. The other constant, C1, we determine by the following condition, saying that approximate again it is, that the net mass flow across any cross section is 0. And so, what he is effectively saying is that the fluid being heated, so it will go up. Then it has finally come down. So actually the fluid profile, finally velocity profile looks somewhat symmetric about it. Actually you can see that the profile would look something like this. We go up, come down, and again we go up. It's going to get, having a double the maximum and the minimum. So what he's effectively saying is that the net mass flow is 0. So it's sort of symmetry. He's sort of imposing a symmetry. It doesn't have to be the case. But on imposing the symmetry, you will get a profile like this. The condition he imposes is effectively rho Pz dy integral dy minus b to d equal to 0. For lack of anything else, he is imposing it. He is saying that the net flow, because you can sort of infer the spread of a circulatory profile, and so he is saying the net mass flow is approximately has to be 0. So part of the cross-section fluid is going up, so flowing in the positive z direction. The other half, the fluid is, the other part you can say, fluid is flowing in the negative z direction. So he says roughly take the net flow to be 0. This is again an approximate condition. On imposing this condition, you will see that C1 equal to 0 on neglecting, because you will see that now you will get terms which are of higher order, of square on neglecting, because that thesis is consistent with the Boussinesq approximation of neglecting, right? Because what we will get is rho is also now a function of temperature. Ez also has a delta T here. So you get terms which will have of the order of delta T square would come in. If you neglect it, which he says is consistent with the Boussinesq approximation, because there we have neglected, and here we cannot consider. So when you neglect them, you will find actually that the C1 would simply become equal to 0, and all you would be left with is this profile. We will take this up in more detail in tomorrow's class and wind up this part of the chapter. Are there any questions? Okay, we've run out of time, so if you have time for questions, you can stay back. Others can please be